Okay, so now we're going to look at differences between nonlinear and linear ordinary differential equations. First order differential equations. So by now you should have at least looked at or seen the existence and uniqueness theorems for both linear and nonlinear, because we're going to be using both of them in this video. So for this first one, it wants us to determine, without solving, an interval in which the solution of the given initial value problem is certain to exist. So I rewrote the problem down here with the initial condition. Now, let's look at this here. So we know, remember from the existence uniqueness theorem, this, first of all, let's define this. This first problem is linear, correct? Because we can see it's in this A of t, B of t, C of t form, right? We have to convert it into our standard form by dividing everything by A of t. We're left with y prime plus the natural log of t over t minus 3 times y is equal to 2t over t minus 3. So that leaves us with our p of t and our g of t, or q of t, whatever. But anyways, from the existence or uniqueness theorem, we know that y of t naught has to equal y naught, right? So our t naught in this case is 1. So that's important to know we're going to need to know that in a little bit, because t naught has to be between our interval of t, right? So because t naught has to exist on, I believe, it's alpha beta, right? Because it only wants to we only have to find the interval of t, because it's the only interval in which this, because it's a linear problem. Remember this? It's linear, so we only have one interval. For nonlinear, we have two intervals. For linear, we have one interval, and that's t. So t is between alpha and beta, where t naught exists on alpha and beta. So we have to make sure that t naught is a value, is either alpha or beta, or a value in between. So we have to find alpha and beta first. So to do this, I'm going to separate p of t and g of t. And we're basically just going to look at just the domains of both of these two functions here. So for the first one, so for p of t, the numerator, for t in the numerator, it has to be greater than 0, right? A natural log, it has to be greater than 0. So we know that t has to be greater than 0 for this point here, right? So that tells us that our interval, well, okay, so let me continue this on. This tells us that t cannot be equal to 3, right? Now for g of t, t just can't be 0, and down here t cannot be equal to 3 again. Actually, t can be all real numbers up here, actually. T can be all real numbers, right? All real numbers. Okay, so now I'm going to rewrite this to be like this. So if t has to be greater than 0, that means that the interval on the top there is 0 over infinity. Now for the bottom, it's just going to be 3, right? I'll put little curly brackets around that. Now for this one, we have all real numbers over, same thing, 3. Okay. So now, where are both of these functions continuous on? Well, this one is continuous from 3 to infinity, right? This is continuous on this, and it's also continuous here, right? Now this one over here is continuous on, of course, 0 to infinity, right? Well, actually 0 to 3, and then from 3 to infinity, right? Break at 3. It should be the same thing for this one here. Sorry. Right? So now, which of these? So now comparing these 4 intervals that we have here, which ones are continuous for both? So instantly we can see these two here are continuous for both. And we also have from 0 to 3, which is part of this one here. It's part of this one here. 0 to 3 is in this interval right here. So, and this one here. So these three things here are what we're going to take. So we know that P and T and G of T are continuous on 0 to 3 and 3 to infinity. Now let's test. Since T naught is equal to 1, our solution is going to exist where? Our solution exists on, remember, this is the existence and uniqueness theorem. It's continuous from, it's going to be from 0 to 3, right? Because that's the only time where we have 1. 1 is between 0 and 3. It's not between 3 and infinity. So we're going to X out this one, right? So this is our answer right here. 0 to 3. That's our answer for this one. So we found our alpha and beta. Our alpha and beta are 0 and 3. So we can also write it like this. Instead of writing it as 0 and 3, we can write it as like this instead. T between 3 and 0, right? Same thing. We found our alpha and beta. And T naught exists on those values there. Okay, so now let's look at the next problem here. We're just going to look at number 5. Forget about number 6. Just scribble that out. Pretend that doesn't exist. Okay, so for this one it says state where in the ty plane the hypothesis of theorem 2.42 are satisfied. Theorem 2.42 is the existence and uniqueness theorem for nonlinear ODEs. So if you remember from that theorem, we know that a nonlinear function is in the form, and that you can see that that's exactly what we have right here. That's what we're given to. So this is screaming nonlinear off the bat. Now we're not given any initial conditions for this one, right? So we don't have to worry about that. We just have to find these the integrals of t and y, right? Or it might not even be a rectangle. It could be like a circle or something. We'll find out because this one looks like it could be. So let's solve it. So now remember, for this one we had to use partial derivatives, right? We had to use partial derivatives for nonlinear. So we have to take the partial of f with respect to y. Now f is equal to 1 minus t squared minus y squared to the 1/2, right? So if we take the partial derivative of this, if anyone has because I know partial derivatives are something you should have learned in Calculus 3, which is typically taken before this class, but sometimes you might end up taking this class without that. So if you're confused on partial derivatives, leave a comment, let me know, and I'll go ahead and I'll make another video just on partial derivatives if you need. But anyways, I'm going to go ahead and take this partial derivative. I'll explain as much as best as I can what I'm doing. So let's look. So we have the partial derivative of this function here. So we're going to do the chain rule. So we take out the 1/2, right? times the inside. That's 1 minus t squared minus y squared. To the negative 1/2, subtract 1. And then we're going to multiply by the inside, but it's only with respect to y. We only look at the y term, right? So this is just going to be negative 2y, the derivative of that term. Okay, so now we can simplify this. So I can already see these 2's are going to cancel. And we're going to be left with, so the partial of f with respect to y is going to look like negative y over the square root of 1 minus t squared minus y squared. And I can already tell that we're going to have a circle here. I can already see that we're going to have a circle here because of the denominator. So if we, you'll see in a second what I mean. If you've taken Calc 3, this is, it'll be very obvious. But if not, that's okay. It's a little bit to think about, but if we now we can look at the domain of the partial. So now if you look at the domain of the partial, let's see here. So we have 1 minus t squared minus y squared is greater than 0, right? So let me write this down. Domain. So this would become t squared minus y squared. Actually, let's do this. Yeah. Let me do this. Is greater than or equal to negative 1, right? Now divide by a negative. Right? The inequality flips, and we're left with t squared plus y squared is less than or equal to 1. Now we know from this that this is, I'm also, sorry, this should be greater than or equal to, right? For square roots. So this describes a circle with everything inside or on the border of, or on the border, yeah, or on the, everything inside or on, yeah, or on the border with radius 1. And the center of this circle is 0, 0. And if you're taking Calc 3, you know where that comes from. But if basically the center is, if we had something like this instead, the center would be negative 1, 0. Okay? But just don't worry about that for this. So now let's read what else the problem was. State where in the ty plane the hypothesis of the theorem is satisfied. Well, this is where in the ty plane it's satisfied, right? This inequality right here. This is where it's a circle. So if we draw it out, it'll look something like this. Here's 1, negative 1, 1, and negative 1. Right, we're going to have a circle. Let me see if I can't get this to work. I have a circle. It's kind of an oval, but it should be like a nice, perfect circle with radius 1, right? Center is 0, 0. That's what this inequality here describes. So the hypothesis of our uniqueness theorem is satisfied for any initial point that's inside this circle, okay? Now let's look at the next problem. So once again, we're just going to look at number 9. Forget this one. let's see. So in problem 9, solve the given initial value problem. So now we have an initial value problem for a nonlinear, and determine how the interval in which the solution exists depends on the initial value y naught. So let me rewrite this. Where y of 0 is equal to y naught. So our t naught is equal to 0. All right, so really quick, let's go back here. Let's take a look at the existence and uniqueness theorem again. So let's see. So this tells us if f and the partial of f are continuous on the rectangle, and t naught and y naught exist there, and that's our rectangle, right? And we have the IVP. So f and the partial have to be continuous on the interval of t and the interval of y. Okay. Let's keep that in mind. Let's go back. Let's see here. So we have this. Let's first write out what our f is. So f of ty is equal to negative 4t over y. And now we have to take the partial of f with respect to y. And this would be negative 4t y to the negative 1, right? You see how I did that? Because you only take it with respect to y. So you're going to treat the negative 4t as a constant, pull it out, you're left with the derivative of 1 over y, which can be rewritten as this. So when we take the derivative of this, we're only going to look at this part here, which is just pull out the negative 1, we're left with 4t times y to the negative 2, right? So now that's the partial derivative. So now we're going to find the domain of this partial derivative. So if I do, so the domain of this, we have what, 4t over y squared, right? Well, 4t is all real numbers, so we're going to be from, and y squared is from, that is everything above 0, right? So it has to be greater than 0. Well, not necessarily. But this is just, the whole thing's all, yeah, it's also all real numbers. So this whole thing's all real numbers. So we're going from, well, except this cannot be 0. Right. Y cannot be 0. So we're going to be from negative infinity, and this is all real numbers up here. So it's going to be from negative infinity to 0, and from 0 to infinity, right? This is our domain. So from this, we know that there is going to be a solution. So there is a solution, right? So now we have to go, so this, we can consider this part A. Well, we first see if there is a solution, right? So part A, is there a solution, right? We found that there is one. Because we can see that it's actually true that if you look back up at this one, both of these functions, f and the partial of f with respect to y, are discontinuous at y equals 0. So as long as we have y naught does not equal 0, right? We're not given y naught, but as long as y naught does not equal 0, so y naught has, so we know that y naught cannot equal 0. There will exist, then there's going to exist an interval within t, right? So that the functions are continuous in the rectangle. So now that we have shown that there will exist a solution to this problem, we can now move on to solving it. So let's rewrite this. So now we have to separate the variables, right? Separable equation. So we're going to have dy dt is equal to negative 4t over y. This is dy over y, times y, is equal to negative 4t dt. This becomes y squared over 2, right? Take the integral both sides. Y squared over 2 is equal to negative 4t squared over 2. And this becomes, we can just do this. Y squared, because we can cancel out those 2's. Right? Oh, and don't forget, plus c. And now remember, from my original video, this is really like plus c1 plus c2, and those c's will combine and become just the normal c, or a different constant, right? So now that we have this here, let's now take the square root of both sides, right? So now let's take the square root of both sides. So we have y squared is equal to the square root negative 4t squared plus c. This will become the square root of y squared can be rewritten as the absolute value of y, right, is equal to c minus 4t squared. So now knowing this, that is the absolute value, we can rewrite this to be y is equal to plus minus the square root of c minus 4t squared. Okay? So now, this is basically our y of t, okay? Now, we were given y of 0 is equal to y naught, right? So now let's plug this into the general solution to find c. So, t is 0, which is equal to y naught, is equal to plus minus the square root of c, right? Because t is 0. So then this can be rewritten as, because we want to solve for c, so we can square both sides. So y naught squared is equal to c then, right? Yep. So y naught squared will be equal to c. So then that'll give us that y is equal to plus minus the square root of negative 4t squared plus y naught squared, right? Or y naught squared minus 4t squared. But so now that we have this is our solution. I should rewrite it like this. Technically, that's a function of t. So now from before, right? We know that. Let me look. We know that y naught cannot equal 0. So we know that y naught cannot equal 0 from before, right? So we have to analyze what's going to happen. We have to analyze what happens to the intervals for like the values where y naught is less than 0 and y naught greater than 0. So let's do this. So let's look at the inside here. So y of our square root, y naught squared minus 4t squared is greater than or equal to 0. This is if we move that over, that'll be y naught squared is greater than or equal to 4t squared. Take the square root of both sides. This will become y naught. Take the square root of both sides. This will become y naught is greater than or equal to 2 times t. So now that we have this, we're going to look at both cases now. So if y naught is greater than 0, we're going to have, well, this is for when y naught is greater than 0. Let's solve for t. So we're solving for the intervals of t, right? So y naught over 2 is greater than or equal to t. if we're looking at both of these intervals, the only thing that's going to change is if y naught is positive or negative. All this is saying, this is just saying negative y naught, and this is saying positive y naught, right? So all that we're going to have here, since t naught is less than the positive y naught, we're going to have this. So then it's going to have to be greater than the negative y naught over 2. Correct? So we excluded 0 for this. So we will have... So this is for our case where where y naught is greater than 0, okay? Now when y naught is less than 0, so this is 0 to infinity, this is would be less than 0, so negative infinity to 0, right? So then we're going to be left with, for this one, all we're going to do is just flip it. Actually, I just realized something. Let me so for when y naught is greater than 0, we should actually re-look at this. Hold on, I'm sorry, because you can think of it like this: when y naught is greater than 0, that tells us. Well, let me re-explain this. I realized I could explain that better. So if we have y naught greater than 0, right? So that's from 0 to infinity. We'd have to know that the absolute value of y naught has to be equal to y naught, right? Because it has to be positive. So knowing that it has to be positive, we're gonna have the 2 absolute value of t. So then when we solve for t, it's gonna look like right? This absolute value changes everything. This is why we're able to because we know this absolute value of t is less than or equal to y naught over 2. That can be rewritten as this is a better way to explain it. That can be rewritten as right? So that'll tell us that like t exists on this would be closed bracket negative 0, because it doesn't exist on 0, remember? Y naught cannot equal 0. So it doesn't exist on 0. Union 0 y naught over 2, right? So yeah, and so in this case, this is y of 0 is equal to positive y naught. So if we go back to our solution for our differential equation, for this case, we're going to have absolute value of y is equal to the square root of y naught squared minus 4t squared. So then that gives us y is equal to the square root y naught squared minus 4t squared. So I'm doing a little bit of extra work here, but really what the question asks for determine the interval in which a solution exists. So the interval is well, okay, so the interval is going to be this, basically. This is fine as an answer here, but we're not done yet. So, see, these ones here get a little confusing, as you can see. I'm getting a little bit mixed up here too. It's been a little while since I've done this, so I'm really thinking right now. So, but anyways, if we have this, we'll be left with this function here, right? This will be our solution. But if we have if we look at now y naught is less than 0, we're going to have something like, right? So then, right? So that, because we're going to have, yeah, we can divide by that negative. Well, no. Let me just solve for t. So absolute value of t would be less than or equal to negative y naught over 2, right? So this, all it's going to do for us is it's just going to flip what we had before, right? So then t exists on, this is the same thing, it's just going to be flipped. Union 0 negative y naught over 2, close bracket. So in this case, we would have something like this. Right? But in this time, the absolute value of y is not just equal to y. It's equal to the opposite. So it would be negative y. Right? Because you can think of it like this. Think of it like this. I should have said this before too for the other one, but for this one we're going to have like y naught less than 0. So that's going to tell us that. Okay? So the negative y is equal to the absolute value y naught squared minus 4t squared. So therefore we have just a negative value. So our intervals here would be okay. So this is our intervals here over 2, and we have this one was for right, and this one's for positive values. Okay, so like with the is this going to say uniqueness theorem for first order nonlinear differential equations, right? We show that there's a unique solution to the given initial value problem. That's what we did before in the first part. We showed there's a unique solution, and then we found it using the method of separating variables. So our unique solution is actually, let me see. This can be considered the unique solution. Or where was the answer to our, okay, so we actually have two unique solutions, I guess. This is one, and this is the other one. Oh, I forgot to move that negative over. Right? So we have two unique solutions. Okay, so once again, we use existence or uniqueness theorem for first order nonlinear ordinary differential equations. We show that there's a unique solution, and then we found that using a method of separating variables, and we prove that it does exist.